Okay. So now there are two theorems on the moment of inertia. This helps us to analyze many things are answered, and therefore these two. One is called perpendicular axis theorem. Other one is the parallel axis theorem. Okay, right. This will help us to simplify the calculations. That is the main purpose of this. Okay. Anyways, we will derive these two theorems from the basics. So there goes the derivation, as you can see here. Anyway, I will explain this. Now, will you please follow me, all of you?
Yes, sir.
Right?
Yes.
Now, parallel axis theorem. Parallel axis theorem we are going to derive. Okay, we are going to derive this formula. Now, what you see here is this is a rigid body, and you can see here this is the center of mass. Right? Hello. This is the center of mass. Now, so far, whatever discussions we did here, you can see all these discussions. The axis is passing through the center of mass. You can see here the axis is passing through the center of mass or centroidal axis. Okay. Now here, what if the axis is passing not through the center? It is somewhere here, or the axis is somewhere here, or the axis is somewhere like this. Okay. So we need to find it. I suppose you understood that.
Yes.
See, I can rotate it with n number of axes. Now this is axis number 1, axis number 2, axis number 3, axis number 4, axis number 5. Okay. Anyways, I can do the axis. Okay. So now we will try to find out the way how if the axis is not passing through the centroid, and if it is not perpendicular, how to go about calculating the moment of inertia. And that is more realistic, because always the axis need not be perpendicular to the, it need not be perpendicular, and it need not pass through the center of mass. That is more realistic case. So we'll have to deal with it. Okay. So therefore, we take an arbitrary diagram here. You can see here, this is an arbitrary diagram here. And what you see here is this is the rigid body, and you can see here point C. Point C is what? The center of mass. Hello? Now, the axis, if it was passing through the center of mass, okay, then the formulation was different. Okay, you will get the axis of rotation to the center of mass. Now, I am going to choose an axis at this point P. That means now I have got this rigid body. Assume that this is a planar. This is a planar rigid body in the shape of an oval, and the axis through the center is perpendicular to this plane, and the axis through P is also perpendicular to this plane. Can you imagine that?
Yes, sir. Yes, sir.
So now, what is meant by finding out the moment of inertia? See, moment of inertia is from this axis how the mass is distributed. From this axis, how the mass is distributed. Okay. So, depending upon the pattern in which the mass is distributed, you are going to get the moment of inertia. Okay. So there is no harm from you. See, here if I hold it, the moment of inertia is more. I suppose all of you can appreciate that.
Yes, sir.
Why it is more?
The distance is increased.
The mass is distributed far away from this axis.
Yes, sir. Yes, sir.
Okay, and if I come here, you see, so much mass is here and so much mass is here. So the distance from the mass, not the vectorial distance, the distance from the axis of rotation is small here. If I take it at the center, then these masses are close proximity with the axis, and therefore the moment of inertia is less. Okay. So here you see the axis passing to P. Now I am considering an incremental mass dm. You can see dm here at a distance capital R from P. At a distance capital R from P. Okay. Now if it was about the center, then the integration would be what? Integration dm, okay, into r cube, where r is the distance of dm from the center.
Yes.
Okay. So now we will make use of the triangle law of vector addition, and we'll write this capital R because we want to know the proximity of dm from P. Okay. So we want to know this. So therefore, what I'll write here, this capital R, I'll write it as R, this R bar, okay, plus R plus, see, R bar plus R dash bar. This is R dash. Understand? So, so I start my journey like this. So you can see here, IP is equal to integration R square dm. Can you appreciate this?
Yes.
Only one student is saying yes, sir. I want yes from everybody.
Yes, sir. Yes, sir.
IP is equal to R square dm. Now this R square, we'll write it as R bar plus R dash bar modulus square. I suppose all of you appreciate this.
Yes. Yes.
Then we open the bracket. So this we get R square plus R dash square plus 2 R bar dot R dash bar. So IP is equal to integration R square dm is equal to integration R square dm plus R dash square dm plus 2 R bar dot R dash bar. Same, just we are using the mathematics and just we are writing it. Now here you see, as R is a constant. Why R is a constant? Because from this point P, P is fixed point and C is also fixed point. So therefore this R is constant. Okay. So therefore integration. So one by one integration we'll see. The first integration. R square dm, R square is common, so I'll pull out R square, and integration dm. Integration dm is the total mass. Yep. Okay.
Yes, sir. The R bar plus R dash bar, how R square plus R dash square, to cos it is not the.
Why you want? No.
Oh, okay. Sorry, sir. Sorry.
Okay. Followed?
Yes, sir.
Yes, sir.
Now one by one integration and see. So first R square dm, we got it as mr square. Now 2 R bar dot R dash bar dm. Again here, this integration I can write it as 2 R bar because R bar is constant dot integration of R dash dm. Okay. So what is R dash? Proximity of dm from the center of mass.
Yes.
Now you see here, R dash dm is equal to RCC, means the RCC is what here? That is, you see, RCC means this incremental mass, the proximity of the incremental mass from the center, from the center of mass.
Sir, but how are the taken term functions?
Which one?
Like RCC machine.
That is what. I'll explain it. Okay, that is why we have not designated this as R dash and taken it out. You can see here, we did not write, we did not designate it as R dash and take it out. We designated it as RCC and took it out. Can you appreciate that? Hello?
Yes, sir. What is that?
I will tell you, yeah. First of all, you appreciate that. See, instead of R dash bar, we took it out as RCC. Right? I'll explain. Integration dm. Now, what is this? This will be equal to 0. Now, don't bother what is this RCC, but let's simply bother about this as a whole. What does it mean? That means now, now you see, you remember we took a rod. Hello? We took this rod and we calculated the center of mass of this rod. You remember? The center of mass of this rod was somewhere here. Correct? How did we do this? You remember? We took moment of the masses. Right?
Yes.
Moment of the masses. So
Yes.
this was m1 and this was r. And similarly, you have m1 here and the same distance r1. If you take this as a uniform product, that means the moment of the masses about that point is 0.
Yes.
And that point becomes what? The center of mass. You remember? That is summation mi xi. Okay, summation mi xi. Okay, and if you are addressing this I with respect to C, the center of mass,
Yes, sir.
then this will be equal to 0.
Yes.
Got it?
Yes, sir.
So therefore, in this diagram there, we got here r dash bar dm. Integration of r dash bar dm. What is r dash? R dash is same as this x. The proximity of the dm from the center of mass.
Yes.
Yes.
Understood? So this r dash now I will write it as rcc. That means, so it is the distance of the incremental mass from the center of mass. Okay, and therefore integration of r dash dm will be equal to 0.
Yes.
Moment of the masses.
Sir, why did they take R bar CC comments directly could have written that it is 0?
Yeah, directly they would have written. We have written that because further we are going to make use of this symbol for some other reason, but just don't bother about it. So you can directly write here integration r bar dash dm is equal to 0.
0, yes.
ठीक है?
Yes.
Right. So this term 2 r dash dot r dash dm will become 0, right? And integration r square dm is nothing but m r square, right? Because this r is also constant from here. The small r is also constant.
Yes, sir.
Now comes the second term. What is the second term here? R dash square dm. See, r dm is constant. That is moment of the masses. Got it?
Yes.
Hello.
Yes, sir.
But r dash square dm will not be equal to 0.
Yes, sir. Yes.
Right?
Yes.
So therefore, we end up writing ip is equal to mr square plus r dash square dm. Now substituting r dash square dm is equal to ic. R dash square dm is what?
Yes, sir.
The moment of inertia about the center of mass
Center of
Yes.
as ic. So we get here ip is equal to ic into mr square. So what is ic? IC becomes the moment of inertia of the body about the center of mass, and m is what? The mass of the body, the total body m. And what is r small r? The proximity of the point, the axis point, which is parallel to the axis passing through the center of mass, okay, and the perpendicular distance between the two, r.
Yes, sir. Yes.
And this is nothing but the parallel axis theorem.
Yes.
Yes, sir.
Did you all get it? Did you derive it earlier? So you only accepted it. Now you see you can derive. Why I am showing a derivation is because now based on this derivation you will have very interesting numericals to solve. Okay, so the knowledge that you have acquired while you have derived this goes a long way in helping you to tackle many issues. Alright friends?
Yes.
Fine, very simple. This diagram is extremely important.
Sir, so it implies that moment of inertia about COM is always the minimum. Sir.
Yes, obviously. Obviously. Very good abstraction. Very good. I think somewhere I have marked it. So another way to look at this one is like this. This theorem is also known as Steiner's theorem and can be used to determine the moment of inertia about any axis if the moment of inertia of a body about a parallel axis passing through the mass center of the body and perpendicular distance between both the axes. That is important.
Yes, sir. Yes.
So therefore, you write it as IO. IO is what? The moment of inertia about some reference point. O, reference point O will be the moment of inertia about the center of mass plus m into XE square. What is XE square? Here it is shown as R. XE becomes what? If you take O as the origin, XE becomes the perpendicular distance of the center of mass of the body from the frame of reference.
Yes.
Got it? So therefore, the moment of inertia about any axis parallel to the axis through the mass center is given by the sum of the moment of inertia of the axis through the mass center and product term of mass of the body and the square of the distance between the two axes. I hope everything is clear here.
Yes.
Okay. Similarly, you have perpendicular axis theorem, right?
Yes. Yes.
So just read out this. The theorem is applicable for rigid body that lies entirely within a plane. That means you please appreciate that theorem of perpendicular axis is for laminar body. It should be a laminar.
Yes, sir. Yes.
Right? Right? Or a rod bent in the shape of a plane curve. The moment of inertia Ix, Iy, Iz of the body about XYZ axis can be expressed like this. For a planar body, the moment of inertia about the axis perpendicular to the plane of the body is the sum of the moment of inertia perpendicular to the axis. I hope the statement was quite clear and the diagram is quite clear.
Yes, sir.
Now, can anybody explain this? I have got something here. Okay, how are you going to using this? How will you illustrate the use of this perpendicular axis theorem? So this is a planar body. Come on, somebody.
Sir, now if we consider an axis, if the planar body rotates about an axis.
Okay, first. Okay, now supposing I give you a planar body. Okay, so this length is A and this length is D. Right? Mass is M. Right? So I give you these things. Now demonstrate the use of perpendicular axis theorem for this. So can you find the moment of inertia about the center of mass here for this body?
Yes, sir.
Find out. For this body, what is the see, now you know the center of center of mass is this. Very good. Human is good. The center of mass is this. So what is the moment of inertia here?
M into S
By 12 into I square plus B square.
M into
plus B square by 12.
M into means M, open the bracket, A square plus B
A
square
square plus B square divided by 12.
divided by
1 times.
12. Right. So,
Yes, sir. Yes.
see, now gentlemen, again you see, you should tell me about which axis, man.
Sir, about an axis that is coming out of the plane, so like Z axis. Yes.
Yes, about Z axis.
Perpendicular to the plane, yes, sir. Sir,
This is
through the center of mass, passing through the center of
Into
mass.
the board, sir.
into the
Yes.
board. Acha. So this one is IC and into the board or out of the board.
Yes, sir. Yes,
Yes, sir. Yes.
You should tell it. So all of you are sure you got this?
yes, sir. Yes, sir.
Yes, sir.
Wonderful students. Wonderful students. Right. So that means now this planar body, now I am going to hold my hand here, right? And I am going to rotate it. So the axis is right here and I am going to rotate it like this. So you have found out this to be equal to m into a square plus b square divided by 12 about this axis. Correct?
Yes.
Excellent,
Yes, sir.
excellent students. Now I want to know, listen here. What is the moment of inertia about this axis?
M by 12 into S.
M by 12 into a square. How did you get it?
Sir, it is similar to rods, sir. which is rotating about its center of about an axis passing through center of mass.
You didn't demonstrate the perpendicular axis theorem.
Sir, like same method, sir. Like I considered an axis parallel to the length, sir, one parallel to the breadth, sir, and the third axis will be perpendicular to the plane and passing the center of mass. We don't go up closer, we can find.
So you found out this, and you found out this. So this is this, and this is this part, and then you added up.
Yes.
Okay. So you will call this as IX axis, and you will call this as IY axis, and this one you will call it as IZ axis.
Yes.
That's precisely what you do. Correct?
Yes, sir. Yes.
Excellent. Excellent. Okay. Fine. But anyway, if I give you some planar diagram here, okay, and I say this axis is passing through some point here, perpendicular. This axis is passing through some point perpendicular, and what is the moment of inertia about any two axes, like this. So you will take it as Ix and Iy, and do it like this. That is, Iz will be equal to Ix plus Iy. This is what we do. Correct now?
Yes.
Right. So in general, can you
Yes.
prove Iz is equal to Ix plus Iy?
We can do.
How?
Only for planar body.
Planar bodies.
Sir, like I would repeat, sir, like why is it coming?
Yeah. Can you prove this by taking some arbitrary body?
It's just Pythagoras theorem.
Excellent. It is just Pythagoras theorem. Brilliant.
Yes.
Brilliant. So here you see it is dm into r square. Okay. So this dm into r square can be written as x square plus y square. So if you take this as r here, okay. So this can be x square and x and y.
Right.
Okay. So dm into x square will be ix, dm into y square will be y, and this will be equal to I. Excellent. Okay. I hope everybody got this clear.
Yes, sir.
Yes, sir.
See, it's important that you also try to dig yourself into and find out like how did this come, because your examination questions will be around that aspect, how well the student has understood this concept, okay, and how well he can apply this concept, okay, under different circumstances. Okay, so that's what is the that's how we have to look at it. Anyway, we just did this. Then there is something called radius of gyration. Okay. Do you know about radius of gyration?
Yes, sir.
Okay.
Yes, sir.
Other than Srijan and Om, and Sushant and Neelas, others, can you tell me what is this radius of gyration? Yes.
This is the distance from the center of the rigid body where you can consider the center of mass is situated. So we can equate it.
Again, come again.
So like this is the distance from the center of the rigid body, sir, where we can assume that the entire of the mass is concentrated at that point. Sir.
Okay, fine. That means now, you see, if you good, very good. So if this is a disk of mass m and radius r, and if I am considering this axis of rotation, okay, passing through C here, okay, then the moment of inertia of this will be mr square, right? Mr square by 2. Clear? Hello?
Yes.
Now what I do, this entire mass, I will convert this entire mass into point mass. I will convert this entire mass into point mass.
Yes, sir.
And taking the same axis, I will keep this mass here. And that is, I will take this distance as small k. Now, what is it now? If I want to rotate this mass about this axis, then what is the moment of inertia of this mass? That is, I want to rotate it. Okay, then by basic definition, the moment of inertia of this mass, this point mass from this will be m into k. Now I have chosen this K in such a way that the moment of inertia of the original disk is still the same. This is the moment of inertia of the disk. And if I convert this mass into point mass and situate it at a strategic distance K from the axis of rotation, alright, then I am going to equate it like this, and what I get here is that K will be equal to R. Okay?
Yes.
Yes.
Got it?
Yes, sir.
Yes.
Somebody
It
told.
need not always be access.
Wait, need not always there, but have I getting it correct? For a disk it is mr square.
For a disk, it is MS by 2.
Mate? Sunda kutirala. So it will be K will be equal to
Root R by. Sorry, R by root.
R by root 2. For the disk. Okay, this is for disk. Now the same thing if I take a loop, hook, then it will be m square, that is I have considered this hoop or the ring of mass m, and this is R. So in this case it will be ms. And here in this case the radius of gyration, this is called radius of gyration. The radius of gyration K will simply be equal to R.
R, yes.
Okay, you will see the use of this. You will see the use of this, why we are going to use as we develop further theory in this subject. Right? And see, for a hollow sphere it is 2 by 3 mr. Okay, that is, this is a hollow sphere about this axis. Now I convert this entire mass into point mass and keep it somewhere there, m is. So in this case, you see the radius of gyration will be r into root of 2 by 3. Okay? Like that, you are going to make use of this. And if you are very inquisitive where this will be used, okay, I'll just give you a hint. I'll be doing this, dealing with this theory later on, where you will find a lot of usage of this. Okay? See, my dear friends, supposing this is a, anything, slide, and I keep the object here. I keep the object here. So I keep the object here. So what happens? This object of mass m at height h, okay, will be having potential energy mgh. Got it?
Yes, sir.
Now, if I leave my hand, what happens? This mass will come down here.
Yes.
Yes.
Okay, see, that is, supposing it is in a shape in by which it can roll and come here, rolling without slipping and coming here. Supposing you had kept a dabba here, then you could have simply slided and come here. You got it? So in that case, supposing I had kept a dabba here, then when it comes to this point here, what is the velocity at this point? So immediately you get half mv square.
Root 2g.
Okay, so you get root 2g. V will be equal to root 2g. Very easily. Now instead of the dabba, if I keep it as a in the form of a cylinder, and then by the time it comes here, then the total energy here will not just be the kinetic energy of translation.
Yes,
It will also be rolling and it will be coming.
Yes.
So the total energy here, mgh, will get converted into kinetic energy, and this will be equal to half m v square plus half
Plus half
I
How
omega.
carry omega square.
I will be dealing with this theory, so you will
Yes.
see that it is having both, right?
Yes.
It is having both. Okay. So when we are dealing with these types of situations, we need to use the concept of radius of gyration, and things will become much clearer. Supposing I will take 3 bodies of same mass, cylinder, sphere, and a disc, and I keep it at the same height and allow them to roll down. Then which of them will reach the earth first, the foot first, and which one will have more velocity, translation velocity. Issues like that, we can handle using the radius of gyration. Okay, there are many more applications of that. We'll deal with them. Right. So find the moment of inertia of uniform disk of mass m radius and about its diameter. So can you find out about its diameter?
Yes.
Yes, sir. MR
Don't. So,
Yes.
so this one about this axis it is for a disk it is mr square by 2. Now they are asking about the diameter. Okay. So about the diameter, now you will use ix plus iy is equal to ic. So in this case, across both the diameters which are perpendicular, okay, it is same. So you can take it as 2ix is equal to iz, and iz is equal to mr square by 2, and therefore ix will be mr square by 2. mr square.
Yes.
Very simple. Not at all difficult. Okay, fine. Okay, friends.
Yes, sir. Yes,
So
sir.
we could all do this. We can do it. Now, among all the parallel axes of moment of inertia of a rigid body, about the axis through which the mass center is minimum. Somebody abstracted this. The moment of inertia about the center of mass is always minimum. Otherwise, mr square will get added. The second term added to the moment of inertia I see about centroidal axis of object can be recognized as moment of inertia of particle equal to that mass is located in it. It reveals that the plane motion, the rigid body is superposition of pure rotation and of the about the mass center or centroid and the translation of its mass. Anyway, we'll deal with it later.